Hello, my name is Maria Eduardo Andrada, and today I would like to talk about my paper named Testing Different CNN Architectures for Semantic Segmentation for Landscaping with Forestry Robotics, co-authored with my supervisors João Ferreira, David Portugal, and Michael Couceiro. In this presentation, I will firstly introduce the subject, what are our limitations, our aim and objective, and the restrictions we have. Secondly, I will briefly explain the similar work to ours and why our contribution is still important to the field. Then, I will describe our approach, how many classes we are using, which architectures and evaluation metrics we chose and why, and the type of image we're using. Afterwards, I will show all our results based on each experiment conducted and our discovery from them. First set of sets was to discover if transfer learning is possible. Second, which are the best parameters for each architecture. Then I will compare the best results of each architecture and inference time and discuss our final choice. Lastly, I will discuss what we concluded and what are our plans going forward. Forestry robotics has great potential, although it's still in the very early development stages. One of the reasons why is its limited perception capabilities due to lighting and the sensors available. As you can see in the sample image, it is a dark image. It's hard even for a human to be able to identify the humans in it or differ the path from the trees. In this project, we propose the development of a multi-robot system to reduce accumulation of live combustible material using semantic segmentation. Specifically, our aim is to semantically segment the image as to identify any flammable material on the ground that our robot can clean it up, such as bush. That will be the red label in the image. We also need to be able to differentiate between the flammable material and what is not supposed to be cut down, such as the trees in green here. Those need to be protected and avoided. Lastly, for safety measure, we need to also detect people and animal to avoid any catastrophic mistake. That will be the horse in purple, for example. We have some important requirements to achieve our goals. Those are to use multispectral or NGR images, which uses near-infrared green and red channels instead of the usual RGB, red, green, blue channels as the input image and depth information. Next, to avoid any damage to fauna or flora, we should be able to minimize as much as possible the number of false positives for the fuel class or flammable material which we would like to cut down. The image representation here is an example of one of the architectures we used in this paper called Adapnet. This is a simple model in which shows that the encoder, the green, convolutes with batch normalization before entering the eASPP layers in yellow, in which two layers, the skip layers, do not. The output of eASPP goes to the decoder with the skip layers to identify the classes needed, as you can be seen in the output. Regarding any related work, it is hard to find any work that uses similar technique, semantic segmentation, in forestry application at ground level. Most of the work found involves satellite image for crop identification and such. However, we found one very similar to our requirements, an approach developed by Valada, in which they developed their own multimodal CNN, which takes into consideration depth and RGB image as input to output a number of classes in forestry environment. However, their focus was to identify classes without any dangerous tasks, such as ours, and did not include any of our classes. Not only that, but also our work would use ROS as our main software. Therefore, our contribution will be the focus on how to minimize false positives while using the robot in real time using ROS. To achieve the requirements, we decided to segment for 6 classes, as it can be seen in the sample image. It includes classes for humans and fauna, purple for animals and yellow for humans, flora, green for canopies, brown for trunks, and the flammable material in red. The last being background in black for anything that is not the previous 5 classes. We utilize the NGR images trying to achieve 10 frames per second for real time. If the robot moves fast, it could easily avoid humans or animals in that frequency. For the segmentation, we decided on 3 different architectures to compare. MobileNet v2, made for speedy applications and lack of graphics. ResNet 50, one of the best architectures at the moment for segmentation. And Adapnet, a modification of ResNet by Valada, as it could be seen in the diagram in the previous slide. Lastly, our approach uses weights and biases to evaluate and benchmark results. It is an online tool for academics to log each step of the way. It shows hardware temperature, memory usage, and also any metrics we would like to see. In our case, we chose these 3 here in the slides, those being Jacquard index or IOU, F1 score, and recall. Those were chosen because IOU compares the true positives in all the possible results, similarity and diversity of sample sets. F1 is a weighted version of IOU, and it measures the harmonic mean of precision and recall. And recall, which measures the quality of the positive matches, which is ideal for a scenario of minimizing false positives. The meaning of the formulas are TP, true positive, or pixels correctly classified, FP, false positive, pixels wrongly classified, and FN, false negative, pixels wrongly indicated class is absent. Now, I will discuss all the results we found. For all the experiments we conducted, we used the GeForce RTX 2070 with a Core i7 8th generation CPU for performance comparison. The dataset used was collected by the SAMFIRE project, in which we labeled 500 NGR images according to the 6 classes discussed above: canopies, trunks, people, animals, background, and fuel. This dataset also has abundant samples for canopies and fuel, but fairly fewer samples for humans and animals especially. The first set of experiments were conducted to evaluate if one of these or both these transfer techniques are applicable. Since most datasets are RGB, it was not known, or there is no work that shows that features would be well transferred when using different input channels. We used pre-weights, which adds weights for each decoder layer according to a pre-trained model using ImageNet dataset. An example of pre-weight transfer learning can be seen in the image. The other technique is class weights, which penalizes a class that does not show up often enough in a dataset. A lower class frequency results in higher weights. We then compared these techniques in all 3 architectures. First results will be qualitative, just visual differences. All results with transfer learning include both techniques, but MobileNet that only includes pre-weights. As it can be seen, the one that benefits the most is MobileNet. Since it is the least robust technique, it has the hardest time identifying anything well. Even fuel, which is abundant in the dataset, is poorly identified by MobileNet before the transfer learning. However, even after transfer learning technique, it has a hard time finding the highly occluded classes such as animals and humans. While it does not misidentify human for fuel, it does for animals. Now, ResNet 50 and Adapnet Plus both achieve much better results before any transfer learning techniques. It shows that higher number of layers prove useful for our case. Even so, after applying pre-weights and class weights, results are the closest to the ground truth, as it can identify human and animals correctly. This shows that a robust architecture will be a better option for our case usage. Now, I will present the proper quantitative results for each of the combinations we made. We did with neither technique, just pre-weights, or both. Now that we found that transfer learning from RGB to NGR is beneficial, we go for the next set of tests, optimization. This is necessary to find the best hyperparameters to achieve the most optimal result. In this case, we use the tool called sweep by weights and biases, in which it uniformly changes all the hyperparameters encased in this slide to find the lowest validation loss. We chose that because it is inversely proportional to the IOU recall values. Each architecture was trained at least 20 times with 400 epochs each time. Each one of these hyperparameters could have a significant effect on the detection's quality, but usually the most important are max and minimum momentum and dropout layers, and batch size. In our experiments, it shows that changes in hyperparameters have a huge impact on the general results. The graphics show in a lighter, faded colors all the IOU values found depending on the hyperparameters modifications, while the darker, contrasting colors show the best results. That is, depending on the hyperparameter chosen, the class humans could be not detected at all at any moment or be a value as close as to 0.4. Same with fuel. At the first 100 epochs, some configurations will not identify fuel at all using mobile net. Another observation we found was that due to the ResNet 50 robustness, it has a lowest variance. However, only Adapnet was able to identify animals in any of the possible combinations. Our experiments showed, using the recall value, that all three classes, humans, animals, and fuel, have high values, which means that the quality of positives are high, and therefore there's a smaller chance of misidentifying one of these three classes as the wrong one. That is ideal, as it is one of our requirements. As it was the case in the IOU metric, only Adapnet can recognize animal in any of its configurations, and it's therefore the most robust solution so far. As a visual reference, this slide shows the one image with the best results of each architecture to be compared to the ground truth. While the ResNet values were high for humans in recall, they were low in the IOU because it overestimates how big the people are. For our case, it would be okay to overestimate people as to avoid hitting them in any way. However, Adapnet and MobileNet seem to be closer to the ground truth, which is a better result. The biggest issue with this image is to misidentify fuel as a pole as it would try to cut something it should not. And only Adapnet seemed to identify it correctly as background. This slide shows the mean value, inference time, and complexity for each of the metrics from the hyperparameters configurations of the CNNs. As it can be observed, Adapnet has the best overall results with all three metrics. These can be associated to be the only architecture able to identify animals by 400 epochs. It is also faster than ResNet 50, as it has lower complexity. Although it is lower than MobileNet, its robustness compensates. Not only that, but all three best the 10 frames per second requirements, and any faster speed will be wasted. Even though we achieved good results, the system could be improved as the IOU for both humans and animals are still too low for autonomous usage. In conclusion, I spoke today about our motivation to clean the forest using perception, our proposed approach of using 6 classes in NGR images using semantic segmentation, and our results of transfer learning being beneficial even with different input channels. We then compared to find the optimal hyperparameters and compared 3 architectures to see which one suited our aims the best. In the end, Adapnet was the most robust and comprehensive encoder for our application, and we will be using it from now onwards. However, we still need to improve our system to identify humans and animals better. And therefore, in our future work, we intend to add a depth encoder to overcome NGR limitations. Thank you for your time.